And we will continue with the next presentation from Dr. George Markou, who is an associate professor at the Department of Civil Engineering at the University of Pretoria, and an expert in machine learning algorithms as well. He will give us a presentation on engineering simulations, machine learning, and the development of design formulae in civil engineering. The floor is yours, George. Thank you very much.
Thank you, Leah. Thank you very much. Ari, if you can stop sharing your screen, so I will be able to share mine. I would like also, until I'm able to share my screen, to thank Elias and Giarnet and EuroCC Greece for the opportunity and the organization of this event, which is definitely very interesting. So I will be talking about engineering simulations, machine learning, and the development of design formulae in civil engineering. Of course, the work that we've done with Dr. Nikos Bakas and Professor Papadrakakis. Nico, can you allow me to share the screen, because Aris is still sharing his screen and I'm not able to do so?
Yes.
Thank you. Okay.
You should be the host now.
All right, great. This will stop there. Yes. Okay. Let me see screen 2. All right, great. Okay. Can you see my screen?
Yes.
Yes, perfect.
Excellent. All right, great. Thank you. So without further ado, okay, let me. All right, great. So I will say a few things, introductory things about machine learning, AI, and the overall objective of this research work that we've done thus far with Dr. Nikos Bagas and Professor Papadrakakis, including other, of course, associates. I'm going to say a few things about replacing experiments with advanced finite element analysis modeling, something that actually complements Professor Vissarionos Papadopoulos' work, which is very, very important, given the fact that when we work with machine learning and artificial intelligence, in order to replace finite element analysis, it is very important that we know that our software is able actually to predict something that will make sense. And in this case, model nature. So I will say a few things there. Then machine learning, I'm going to present to you machine learning algorithms and say a few things about high performance computing and what we've done thus far. And I'm going to show you some results that derived from our research work, and then a few conclusions and the future research that we're going to do. Of course, I'm going to say a few things about current research. I have 20 minutes, so I'll try to talk about everything within the allowed time. So in this case, the main objective of our research work was to develop initially some design formulae through training AI and machine learning algorithms, which I will refer to as ML. And by using large data sets, which we generated either through analysis, nonlinear analysis, or experimental. The problem, though, with experimentally generated data sets is that they are limited in terms of data samples, and usually they are either 100, 1,000, maximum 3,000 data samples, which of course is not ideal. Furthermore, we have inherent errors, errors that result directly from the experiments themselves. And sometimes you can download a data set and you will find the exact same specimens that were performed the exact same date with the exact same geometry, material properties, reinforcement ratio, and so on, if we're talking about reinforced concrete beams. And they have more than 15% difference in their the reported ultimate load. It is also well known that for us to develop robust, reliable, and extendable predictive models, we need large data sets. So in order to do that, we need to produce them, given the fact that performing, let's say, 1 million experiments is not an option for sure. Now, the past in this couple of months, I've received some articles in relation to the development of design formulae and predictive models, and all of them are using 80, 100, 150 data sample data sets, and then they produce, in this case, predictive models. And the main problem with this approach is that the experimental results that they are using were not designed in such a way that the data set will have a good distribution. So most of the data are concentrated in a specific geometry, and therefore this creates also issues with the training. And in this case, researchers get some good results, let's say, in terms of accuracy, given the fact that they do not have very large data sets in order to validate their models, and they still, let's say in this case, state that these predictive models are general. So this is something that definitely has to change. And in order for us to be able to take the next step is for us to build and construct reliable large data sets. And in this case, of course, we need to further the advancement in terms of accuracy and efficiency of the artificial intelligence and machine learning algorithms that we actually use to train our data sets and develop our predictive models. And I'm sure many of our participants today, they came here to see a few things about that, and I will show you a few things in section 3. Now, in order for us to be able to say, we've developed this data set and we've used it to develop a predictive model, then we need to make sure that we have the ability to perform advanced nonlinear analysis and develop these data sets. And those data samples that we produce, they actually represent real life, right? And results that can be, as let's say, assumed that represent the ultimate strength, let's say, of the beam, like we did here from a recent study where we investigated deep beam reinforced concrete beams, which were reinforced with glass fiber aramide and carbon fiber reinforced polymer bars. And we tested also Recon Unfair, which is the software that we used in order to do that with other experimental data, like a 4-story building, which, as you can see here, a P-delta curve, which compares the experimental and the numerical results, and of course, nonlinear dynamic analysis. These are the curves that resulted from the numerical investigation of deep beams, a nuclear reactor building, soil structure interaction problems like this 10-story reinforced concrete building, reinforced concrete pile cap, which is 2 meters thick, as you can see here, of this wind turbine structure, and so on and so on. And of course, if we want to see the corresponding publications that we published thus far in terms of validating the Recon Unfair, these are the journal publications and of course conference publications. I'm not going to read them to you, but we invested a significant effort and resources in order to be able to make sure that our software is validated. And of course, when you have data sets, and these data sets, let's say now they are not 100, or even if they are 100, they consist of 100 data samples. And if in our case, the largest that we've had so far generated is 100,000 approximately, you need to have machine learning algorithms that will be able to result objective and of course accurate predictive models. So I'm going to present to you 5 methodologies in this case. 4 of them actually have been sent for reviewing and through this publication that was done in coordination and collaboration with Dr. Bagas, Savas Hadjikristovlis, and Professor Manolis Papadragakis. And it's titled A General Framework of High-Performance Machine Learning Algorithm Application in Structural Mechanics. Of course, it is very important to state here that these methodologies can be used with any data set, and not only data set that refers to civil engineering related problems and structural problems. I'm going to show you some results here from a high-performance computing training through high-performance computing and image, in this case, recognition. So the first methodology is polynomial regression with high parameter tuning, which we call polyreg-HIT. This is applied to develop predictive models in higher order classes. And of course, the model relies on nonlinear combinations. And the automated procedure in selecting the nonlinear features is also integrated, meaning what? We do not need to define the features anymore, the number of features of the final equation, which is what this methodology does. It actually creates an equation, and we can actually see the equation of the model, right? So instead of saying, I want an equation with 10 members, 10 features, now this is done automatically, and I'm going to show you after Dr. Nikos' presentation in the hands-on applications how this is done through the algorithm, which is Python-based. So in this case, we have a number of nonlinear features, and this is, of course, a very computationally demanding, in this case, procedure. So this requires a selection feature, which is a new algorithm that we propose in this general framework of high-performance machine learning algorithm paper. And as you can see, this polynomial feature selection algorithm is presented here. Given the fact that I have a limited amount of time, I'm not going to explain you exactly how it works, but this is an evolution of an algorithm that was developed by Dr. Nikos Bagas, and now it's been optimized, and we have this the ability to use it in order to develop our predictive models. Now, the second method is the random forest with high parameter tuning, and the random forest, of course, is a popular ML algorithm for classification and regression problems, and it creates a large number of decision trees and combines their outputs to make, of course, the predictions, and it's an ensemble method that combines multiple decision trees to make the prediction and then aggregate the results of all the trees at the end in order to result the best predictive model. And this approach also reduces the overfitting, right? Overfitting is a phenomenon in machine learning where we have, in this case, during the training, if we train it significantly and we overfit, then this model will not have the ability to predict out of sample data. So for the purpose of the RF hit, which is our random forest with high parameter tuning, these are the suggested parameters: number of trees, sub-feature percentage, partial sampling, maximum depth, and minimum leaf samples that resulted from an extensive parametric investigation that was performed for the needs of this publication that is now under review. The third method is the extreme gradient boosting, which was found to be extremely efficient. And of course, in this case, the framework was designed to be fast and scalable. And Dr. Nikos will talk about this in a bit, and the use of this methodology to train in parallel, which is an extremely difficult problem to perform. And we have managed to do that successfully. And of course, this is used a lot in this methodology is used in industrial applications due to its strong performance. And also avoids overfitting. We're going to see that later on. And of course, these are the proposed parameters that we use when we use the XGBoost for the maximum number of rounds, tree depth, the learning rate, sample of trees, and sub-sample. Now, the fourth methodology is the deep learning of artificial neural networks with high parameter tuning, where we combine also MPI with Horovod, and we use the Ray Tree tune module of the PyTorch. And the number of artificial neural networks are constructed by varying the batch size, and of course the dropout ratio, the number of epochs and neurons, and the learning rate.
George, excuse me for interrupting. Because I'm not the host now, can you please close the microphone of somebody talking?
Lincoln, can you let me see? Okay, all right. Okay, I muted him. Apologies for that. So the training of the networks in this case, again, is constructed in an automated manner, and everything is done by the software. And therefore, this is the beauty of the proposed methodology that can use GPUs in parallel in order to train the models. And as I said before, the combination of Horowitz with MPI is proposed, and this is the parallel stochastic gradient descent, the algorithmic procedure, and this is the proposed combination of the MPI and Horowitz in terms of programming. So we have the initialization of the MPI, where we get also the processors as ranks. For each epoch, we initialize and empty the vectors where we will add later on the predictions, and then we have to place barriers after each optimizer step to collect the predictions for each GPU. I'm going to show you some results in the next slide. And of course, at the end, we need to collect and concatenate the all predictions and calculate and compute the mean average, the mean absolute error, and the loss function in order to evaluate the results. And in this case, definitely when you train in parallel, which, as I said, it's an extremely difficult problem, you need to have a good scalability and handling of RAM. And in this case, I'm going to show you the case of 21,397 image data set. Each image is around 5.76 megabyte, a total of 310 gigabyte data set. And this numerical problem for set optimization of 19 million weights, right? So as you can see here, the corresponding speed up is shown on this graph, speed up along the Y and number of GPUs. The maximum number of GPUs that we were able to use were 64. These are Tesla GPUs. And of course, as it can be seen here, the speed up was found to be 28.77 times. So this shows the speed up and of course the efficiency of the proposed parallel algorithm. Now, a very interesting work that was proposed by Bagas et al. Was the gradient free stochastic training of a artificial neural network with local approximation in partitions. And in this case, the artificial neural networks by neighbors have the ability, and this is very, very interesting and a great advancement in AI, the ability to automatically develop and decide what is the best artificial neural network. And as you can see here, this is the pseudocode of the proposed code. I have the link here, and you will be able to see the recording, but also you will be able to find the presentations at the later on stage. And you will be able to get this link and read about it. The sample of the ANN BN models can be seen through this figure. And eventually you end up having an optimum artificial neural network for your training and a predictive model that will have advanced accuracy and efficiency when it comes to predicting out of sample results. So this is definitely very exciting. Now, given the fact that part of the work that I'm showing you here was resulted through funding that we received from EuroCC. Actually, the first EuroCC project, we used Cyclone, and now the current one and the second one, we received funding to use Meluxina, which is, I think, the 5th largest supercomputer in Europe. And the results that resulted from the work of Ms. Ashley, and of course, Dr. Nikos Bagas and myself, we used high-performance computing in order to investigate and develop predictive models that will be able to calculate the fundamental period of steel structures. So, and by also taking into account the soil structure interactions, is a highly nonlinear problem, and not just material, given the fact that we have the interaction also of the superstructure and the soil domain. So we developed different models, as you can see here, and we were able to solve 49,154 different models under modal analysis, of course, by utilizing high-performance computing. Now, in order to do that, we were able to develop batch files, and through this physical parallelization, as it is described here, we were able to create the folders, place the models within those folders, execute recon unfair, get the results after we execute the executable, right, in parallel, and then automatically get the output from the files that they were generated from the finite element analysis software and create automatically the data set. So in this case, we were able to run multiple models at the same time. The largest model that we analyzed, numerical model, was 4.33 billion degrees of freedom. And as you can see here, its stiffness matrix had an 18.75 times 10 to the power of 18 elements. Now, this is the beauty of it. As you can see, Professor Papadrakakis showed you a very nice, interesting graph, which stopped at 10 to the power of 18. But in our case, we actually, that was one of the 47,154 models. So now we do not fit, if you multiply that with the 10 to the power of 18, we do not fit, and we cannot be seen in that very interesting diagram where it showed the strength and power of supercomputers. And of course, that prophecy that we will always need more computational strength, and given the fact that we increase the problems, and we always need more than what we have. Now, the total output size of this project resulted in 10 terabyte of results, and we used the supercomputer for 400,000 CPU hours in order to develop this final data set. Before I move ahead, I wanted to also show you the results from the preparatory stage, where this shows the actual increase and speed up when we physically parallelize this problem. And we used, in this case, 4 models, and of course we used 1, 2, 3, and 4 course, and we got this speed up as it can be seen here, which is almost linear given the fact that it was optimally done, and we did not have to use any preconditioners or any other methodologies that require additional computational cost, and cost, of course, in terms of communication, very well common known problems when we perform parallel analysis through finite element models. And of course, in this case, the available RAM was accounted thereafter at each node, because a high performance computer has nodes, and each node might have, let's say, 256 or like Meluxina 512 gigabyte RAM each, and it can have numerous nodes, and each node has a number of cores. So this is something that we took into consideration in order to optimize the parallel solution of the tens of thousands of models. Now, the results that we got so far are actually results that were compared with design code. Like we developed, in this case, a predictive model that has the ability to calculate the shear strength, the capacity of reinforced concrete beams without stirrups. And we created the data set just by using recon unfair. And the validation, then we trained, right? And then we got the predictive model, and we validated the results by using actual experiments that they were performing in the laboratory. And we found that our predictive models were more accurate than Eurocode and the American code equations, which was extremely interesting. That's why I dedicated one section and talking about the importance of replacing the experiment. And given the fact that the advances in the finite element analysis area are extreme, we have the ability to do that. Now, we develop models that predict the shear capacity of deep beams, which are not only reinforced with steel rebars, but also glass aramide and carbon fiber reinforced polymer bars. It was another recent work that was published in 2022. And we had the ability to develop predictive models and the first of its kind fundamental period formula that takes into consideration soil structure interaction for reinforced concrete structures with shear walls and without shear walls. And also fundamental period of steel structures, including the soil structure interaction phenomenon. And these formulae are the first of their kind because usually we do not have equations that take into consideration this phenomenon, which is very important as we know in civil engineering. But again, I would like to remind you that the algorithms are not just the AI and ML machine learning algorithms can be implemented in different types of problems. Now, another result that we got was the result of developing the first formula of its kind in the world that is able to predict deflection and section rotation of curved steel I-beam. That is not a single design code in the world that provides us with the ability to do that, given the fact that we have extreme torsional effects when we apply loads in this type of beams, in structural members. And of course, we have the Castigliano theorem, but that's very, very difficult to implement. And definitely the development of this type of predictive models will contribute significantly to our civil engineering community and the design of safe structures. And of course, we did create also data sets with experimental data, and we already proposed a predictive model for the calculation of the shear capacity of reinforced concrete columns. Now, I chose to show you a few results from the curved steel I-beam that resulted with the work with Mr. Elvis Ababu. And of course, this work was also extended by Mr. Victor, which are all University of Pretoria students. Elvis is a master's student. Victor was final year research project student. Here we see the validation of the finite element analysis software with actual experiments where the numerical accuracy was 1.5% error, like in this case, the error was just 1.5% in terms of ultimate failure. And this is one of the models. As you can see, curved steel I-beam, deformed shape, and solid von Mises contour. And you can see now the complexity of the deformation and why we were not able as civil engineers so far to develop an actual equation that will be able to predict the deflection, let's say, at the midspan, or the maximum load that we need to apply in order to make this fail. Now, the polyreg was used in this case, and we got a 4.11 average error, 4.11%. And this formula can be seen here. Of course, this is something that needs to be extended, right? Additionally validated, and we need to develop a larger data set, which is the work that Elvis Ababu is doing in his master's. And of course, Victor will also be working in this research project. We already performed an experiment in our laboratories at the University of Pretoria on steel I-beams, curved steel I-beams, and we further validated the finite element analysis softwares that were used in predicting the mechanical response, plus the machine learning algorithm generated predictive models in order to see if they have the ability to actually capture real mechanical response of real structural members. Now, as a conclusion, it is very important that developing large data set is crucial to the development of new design formulae. And of course, the improvement of AI and ML algorithms is also very important. Now we are, of course, able to solve problems that we weren't able to solve before. And we've seen that with different problems that were presented here, which is a very exciting time to be alive, especially as a researcher, being able to solve problems that we could not solve before. The use of high performance computing, of course, is extremely important in the development of large data sets. And the development now of formulae that also take into consideration soil structure interaction effects, like the case of reinforced concrete piles, is performed as we speak. And we take into consideration develop models that will take into account the cyclic behavior and predicting the cyclic behavior of structures. And of course, the idea now, not only just to use ML and AI to replace a part of the finite element analysis, but replace the entire methodology. This is our main goal. So what Professor Vissarion showed you is very important, but our goal is actually to make the finite element analysis obsolete. And this is going to be performed by developing extremely large data samples. And we're going to now develop predictive models that will give us directly the p-delta curve and avoid all the finite element analysis calculations and the loss of time and resources. As you've seen, we need a lot of resources to do that. Now, I would like to thank Thomas Kakavas, Artemis Sarianou, Alexandra Maluda, and Esti Powell for their professionalism, dedication, and organizing and promoting this event. They are great, and it was a pleasure working with them. Also acknowledge the two EuroCC projects that helped us to get the results or part of the results that you've seen here. And of course, a special thank to Elias and GRNet and EuroCC Greece for supporting us, and our team for using Eleuxina supercomputer, and of course for the organization of this very, very interesting event. Thank you so much. That's it from my side for now. See you after Dr. Nikos gives his speech, then we will see the hands-on applications. Thank you very much.